It's mysterious and wondrous. Welcome to the world of relativity. Before delving into the dynamics in relativity, it is very important to clarify the concept of velocity. Additionally, we will introduce a new concept in relativity, velocity. In Newtonian mechanics, if Bob moves with velocity u relative to Alice and Charlie moves with velocity v relative to Bob, then Charlie's velocity relative to Alice is simply u plus v. If velocities could be added this way, there would be no upper limit to velocity. No object can move faster than the speed of light. Therefore, the velocity of Charlie relative to Alice, calculated by simple addition, must be incorrect. So, what is the rule for adding velocities in relativity? Let's derive it. In Alice's frame of reference, Bob moves with velocity u. Draw Bob's world line, which satisfies the equation x equals u times t. Assume Charlie's velocity in Alice's frame is w. Draw Charlie's world line, which satisfies the equation x equals w times t. Now, using the Lorentz transformation, convert Alice's frame of reference to Bob's frame. In Bob's frame, Charlie's velocity is v. Charlie's world line satisfies the equation x prime equals v times t prime. Write down the Lorentz transformation equations from Alice's frame to Bob's frame. Replace the x in the Lorentz transformation equations with Charlie's world line equation, x equals w times t. The resulting x prime and t prime are the coordinates of Charlie's world line in Bob's frame, satisfying x prime equals v times t prime. Through some simple algebra, we can derive the formula for Charlie's velocity w in Alice's frame. This is the rule for adding velocities in relativity. Velocities are added in a nonlinear way. If Bob moves at a speed u relative to Alice, and Charlie moves at a speed v relative to Bob, then Charlie's velocity relative to Alice, w, is given by this formula. This is the formula for adding two velocities in relativity. It's not a simple linear addition. Let's explore the mathematical properties of this formula. First, if both u and v are less than 1, meaning both velocities being added are below the speed of light, their sum will also be less than 1. The proof isn't complicated. Here is a simple derivation. No two velocities, when added, can exceed the speed of light. This fact underscores that the speed of light is an absolute and unsurpassable limit. Next, let's examine another property of velocity addition in relativity. When both u and v are much less than 1, their sum approximately equals u plus v. When u and v are much less than 1, it implies that the denominator in the addition formula approximates to 1. Thus, the result of adding the velocities approximates the numerator, which is u plus v. This property demonstrates the consistency of relativity with Newtonian mechanics at low speeds. Let's consider another property of velocity addition in relativity. When either u or v equals 1, their sum equals 1. This property is the best interpretation of the principle of invariant speed of light. The speed of light in one inertial frame remains constant in any other inertial frame. The mathematical properties of the velocity addition algorithm showcase the uniqueness and wonder of relativity. On one hand, they are consistent with Newtonian mechanics at low speeds, and on the other, they uphold characteristics such as the invariance and unexceedable nature of the speed of light. Draw the world line of a moving object in an inertial frame of reference. Point E is an event on the world line. One can construct displacement vectors from E to other points on the world line. It has been known to us that the displacement vector is a 4-vector, and this 4-vector has an invariant, delta t. Divide each component of this 4-vector by the invariant delta t. The result is still a 4-vector. As the endpoint of the displacement vector approaches E infinitely close, we can replace the delta symbol with the differential symbol d. Similarly, we replace the symbols in the 4 vector. This 4 vector is known as the 4 velocity of the object at spacetime point E and conventionally denoted by the letter U to distinguish it from velocity. The 4 velocity of an object moving through spacetime, which is defined by infinitesimal displacements in both time and space dimensions, is a 4 vector. The velocity we typically refer to is a 3-dimensional vector, also defined by infinitesimal displacements in time and space. So what is the relationship between an object's 4 velocity and its velocity? Can 4 velocity be calculated from 3-dimensional velocity? First, let's examine the time component of 4 velocity dt divided by dta. Substitute the definition of dt. Divide both numerator and denominator by dt. Based on the definition of velocity, substitute the velocities of each spatial dimension. The sum of squares of velocities in each spatial dimension equals the square of the overall velocity. Thus, we obtain the time component of the 4 velocity. Similarly, the spatial component of 4 velocity dx divided by dt can be calculated. The components of 4 velocity in the y and z directions can be calculated similarly. This is the relationship between 4 velocity and the 3-dimensional velocity we commonly refer to. 4 velocity can be derived from 3-dimensional velocity. 4 velocity is a 4 vector, so the square of the time component minus the sum of squares of the spatial components should be an invariant. Let's calculate it. This invariant turns out to be 1. This differs from other 4 vectors, where the square of the time component minus the sum of squares of the spatial components is an invariant, but not necessarily a constant. The components of 4 velocity must satisfy this equation, meaning that when any 3 components of 4 velocity are determined, the value of the 4th component can be calculated.